Hello there, this is AP Calculus Lecture 3.1 where we're going to talk about extrema on an interval, and when I say extrema, all I mean is maximums and minimums. So the extreme values over a particular interval. So you need to have your note print out. You might have it on two separate sheets, but we're going to go over this front and back. Not going to be writing a ton on this, although I'm going to work 3 problems on the first page, and then we're going to work some example problems from the book. So considering this curve, I've got a lot of spots, a lot of points that are on places that we call critical points. All right, so it's defined below. A critical point are places on a graph where the derivative is equal to 0 or undefined. Okay, so you might not be able to take a derivative there. For example, at this cusp here, this sharp turn, but it's still a critical point. So a cusp is a point where the curve abruptly changes direction. All right, so that's a sharp turn. Okay, so the steps to find critical points, we're going to take the derivative, set it equal to 0, and solve. Now, we did that in Chapter 2 to find where there was a horizontal tangent line. So you can see in several of these examples on this curve, several of these points, we have a horizontal tangent line where the slope is equal to 0. Well, we call that a critical point. All right, and then find the values where the derivative is undefined. So it's going to be undefined where the denominator is equal to 0. So you can have, again, most of the time the critical points that we're going to find is where the slope is equal to 0. But also, if you have a denominator that equals 0, that means the derivative there is undefined, also a critical point. So we've got 3 examples on this page, and I'm just going to find the critical points on all those, and I'll do that on my whiteboard here. So example A, we have 4x squared plus 2x minus 2. All right, and let's say f of x is equal to that. Okay, so f prime of x, take the derivative, would be 8x plus 2. We're going to set that equal to 0. So 8x is equal to negative 2. X is equal to negative 2 over 8, so divide both sides by 8, or negative 1/4. And that is our critical point. That is where the slope of the tangent line is equal to 0. And a lot of this, what we're going to be doing in section 3.1 through 3.6, our first step is going to be finding the critical points. So just a super important process. All right, B, we have g of x is equal to x cubed minus 3x squared minus 9x plus 1. Okay, let's take the derivative. G prime of x is equal to 3x squared minus 6x minus 9. And set that equal to 0. We could go ahead and factor this trinomial, but it's probably going to be easier to factor a 3 out of both sides. So divide both sides by 3. I'd have x squared minus 2x minus 3 now is equal to 0, because 0 divided by 3 also 0. And now I can just factor the trinomial. So it'd be x, and it looks like minus 3 plus 1 would work. If we FOIL that back out, it'd be x squared minus 2x minus 3. So what values of x would make each one of these 0, it's going to be -1 and 3. And you do want to list them least to most. That'll matter a few sections from now when we're doing the first derivative test, but let's get used to doing it that way. So -1 and 3, and those are our critical points, which I will just abbreviate as crit. Okay, and our third is h of x is equal to x to the 1/3. H prime of x then is going to be 1/3 x to the -2/3. Let's rewrite that as 1/3x to the 2/3. So this can never be 0 because our denominator doesn't have an x in it, doesn't have a variable. So this entire function, this derivative, isn't going to be 0. However, there is a place it can be undefined. All right, so it is undefined at x equals 0. Right? If you plug 0 in, then you'd have 1/0, which is undefined. That's also a critical point. So again, critical points are where you set the derivative equal to 0 and solve, but if it can't ever be 0, it's possible that it could be undefined at some point, and you need to figure that out, and that's a critical point. All right, I will erase this, and we can go on to page 2 of your notes. Okay, so I've just got some examples of maximums and minimums. So first of all, you can have a local maximum and minimum. Okay, so in this case, we have a local minimum here and a local minimum right here. Okay, it's just local means values around or near the point of interest. Okay, so you can have a local max or min. I didn't put a max. Well, I guess a max here. The max would be here at 0 for this little section, let's say between -1 and 1. Okay, and also we can talk about absolute maxima or minima. The lowest or the highest or lowest f of x, and what we're talking about is the y value. Okay, the smallest or largest y value in an interval. Okay, so I have a curve here, and in class I used to put this up on the screen. But we would have a local maximum here, but you can see that that arrow indicates that this function goes up forever. Okay, so there is no absolute max because it goes up forever. You can't pick a point that is a maximum. But what we've indicated here is that we have an absolute minimum right here at x equals 1. Okay, that function goes no lower than that. X equals 1, y equals -2. So at x equals 1, but our y value, our minimum value, would be -2. And the absolute minimum, of course, we have a point, the point 1, -2. Now, not all critical points are maximum or minimum points. So you can have, a place where the graph goes horizontal for a second and then continues to go up. So, for example, right here, we have a critical point. However, that's not a maximum or minimum, so it doesn't have to be a max or a min. Okay, let's talk about the extreme value theorem. So a continuous function on a closed interval. Closed interval means brackets, all right? Closed interval includes the endpoints. All right, if it has brackets, that means the interval includes the endpoints. So I've got this reversed. It should be -1 to 1, so I'm sorry about that typo there. So between -1 and 1, that interval, so that's between here and here, -1 to 1, the absolute maximum occurs at -1, 2. So right here, the maximum is there on that interval, okay? So it's a local max maybe for the whole thing, but this time we've defined it as an interval between -1 and 1, and that is the absolute max of that interval. The minimum, the absolute min, is at that point 1, -2 here. So that's the absolute min for that interval and also for the entire curve. Now, an open interval does not include the endpoints. So this is important in your homework. We have to deal with both. But if you, we'll get to that down here. But just remember that an open interval, if it has parentheses, not brackets, it doesn't include the endpoints. So the closed interval method for determining extrema, again, that's just max and min. Okay, we're going to evaluate f at each endpoint, and I'm going to work I'm going to work an example doing this. Evaluate f, meaning we find the y value at each critical point, and then the largest y value is the max, and the smallest value is the minimum. Now let's say we have an open interval. Extrema do not occur at the endpoints or where the function is undefined. So for an open interval, you can't have a max or a min if the x value is up against one of these parentheses. Okay? You can only have a max or a min at an endpoint if it's a bracket, because the open interval does not include the endpoints. So extrema don't occur at the endpoints for an open interval. All right, if that doesn't make sense right now, or you're a little fuzzy on that, hopefully as I work example problems from the book, then that will improve. Okay, so our first example is example 3. On page 360. All right, so example 3 says, so the instructions are find the value of the derivative at each indicated extremum. Well, the indicated extremum would be at the point 4, 6 for number 3. All right, and we actually know, you can eyeball this, see how the slope of the tangent line there would be 0. Okay, so what we have to do is take the derivative. So we should end up getting 0 because we have a graph that we can eyeball here. But our function is f of x is equal to x plus 32 over x squared. Now before we take the derivative, let's rewrite this as x plus 32x to the minus 2. Now it's easy to do the power rule. So f prime of x is equal to 1 minus 64x to the minus 3. So 1 minus 64 over x cubed, and we're going to set that equal to 0. All right, so what would make this true, this statement true? What 0? I think it's pretty easy to solve. So you can probably eyeball this and tell that it's 4. But just doing a little algebra here, we could multiply the whole thing by x cubed to clear that fraction. So I'd have x cubed minus 64 is equal to 0. So x cubed is equal to 64, and x is equal to 4. All right, and that is my critical point. All right, so what is the value of the derivative at that point? It is 0. Okay. Let's do number 8. So number 8 says find any critical number. So I don't really need to show you the book here. We have g of x is equal to x squared times x squared minus 4. All right, so I probably would go ahead, instead of doing the product rule, let's just distribute that x squared. So that'd be x to the 4th minus 4x squared. Now we will find the derivative of that. That'd be 4x cubed minus 8x. We're going to set that equal to 0. I could factor out a 4x, and I'm left with x squared minus 2 equal to 0. So what values of x would make this equal to 0? Well, the first one's easy. If it's 0, we have 4 times 0, 0 times negative 2, that's 0. So we have x equals 0. But I have two others. What squared minus 2 is equal to 0? If you want, you have x squared minus 2 equal to 0. So x squared is equal to 2. X is going to be plus or minus the square root of 2. So you have the square root of 2. I'm not really doing them in order here like I'm supposed to, and those are our critical numbers. The values on the graph that make the derivative equal to 0. So give you this. These are the values, the x values that would give you a horizontal tangent line. Okay, let's take a look at number 18. So number 18 is probably the most important example for the homework. You're going to refer back to this one for the most number of problems. And we're to determine the absolute extrema for these functions, and we have f of x is equal to x cubed minus 12x and the interval of interest is in between 0 and 4. That is a closed interval. So what you're going to do is, if you go back to your notes, I gave you this process. We're going to evaluate the endpoints, f of the endpoints, and then find the critical point. Okay, so first of all, our left endpoint, so I'm just going to call that LE, would be f of 0. So plug 0 in, and that is 0. Our right endpoint is f of 4. That's going to be 4 cubed minus 12 times 4. That's 64 minus 48. That is 16. And then we've got to find a critical point. So f prime of x is equal to 3x squared minus 12. We're going to set that equal to 0 because we don't know what our critical point is. Let's factor out a 3, and I would have x squared minus 4 is equal to 0. So our critical points are going to be 2 and negative 2. However, negative 2 is outside of the interval of interest. So I'm only going to have to look at the critical point 2. So f of 2, so our critical point evaluation, f of 2 would be 2 cubed minus 12 times 2. So that's 8 minus 24, so that's negative 16. So our max occurs at 16. It's the biggest y value. Our min occurs at negative 16. So we've got to do it in point form. So our maximum for this function between 0 and 4 occurs when x is equal to 4 and y is equal to 16. That's right here. Okay, x is 4, we plug that in, y was 16. Our minimum occurs when x is equal to 2 and y is equal to negative 16. So for our left endpoint, that's neither a max or a min at 0. So the minimum occurs, so this curve, the way it goes, the minimum occurs at 2 in between this interval, and the maximum occurs at 4. All right, so that's the example you're going to refer back to in order to do quite a few homework problems. All right, number 32. So 32 is right here. And 32 is what I want you to look at to do number 29, 30, and 31. Okay, so 32 is an open interval. Those circles mean that it's an open interval. So let's just draw it out here. So I've got A, B, we're up here, and so this is part 32A. And it doesn't have to be exact, but it's a declining function to there. And the question is, determine whether f has a minimum on this interval, this open interval a to b. Well, it doesn't, because the minimum occurs at an endpoint, which you cannot include on an open interval. So the answer is, for 32a, there's no minimum. Okay, the lowest value between a and b occurs here at the endpoint at b, because it's declining function the whole time. So there's no min, there's also no max. Okay, there's no max here because the maximum also occurs at the endpoint. All right, let's give an example, though, on an open interval where you can have a max or a min. So that is B. All right, B at A and at B here. We've got our open endpoint. We have our declining function over here to B. But we have a point in between the two that is below when the y value when x is equal to b. It's lower than this right here at the end. Let me draw that a little bit where you can tell. Okay, this point is below that point. Okay, so the book draws it better than I do, right? This point here is below the end point, either of the endpoints. So the answer is yes, there is a minimum, and it occurs at this value right here. If, on the other hand, we had a point right here on this function, we could say, yes, there's also a maximum because it's above the end point right here. Okay? So that's how you deal with an open interval. You can't have maxes or mins at the end point, but it's possible to have one that's in between, depending on how the function goes. But if it's an always declining or always rising function, then you won't have a max or a min on an open interval. All right. So that'll help you answer 29 through 31. My last example is 34, which will help you answer 33 and 35. So 34, and we've got an A, B, C, and D here. So I'm going to draw this, but we want to know what's the absolute extrema, meaning what's the maximum and the min of the function, and it gives closed intervals, partially closed intervals on B and C, and open interval. And so we've just got a declining function like this. This is 4, this is 1, and this is 4, and the y value there is 1. So we've got a declining function there. Part A, we want to find the max and min on the closed interval 1 to 4. Well, we get to include the endpoints. So the maximum occurs at the point 1, 4, because we get to include that. Because the highest value, the highest y value is 4, and it occurs at the point 1. The minimum on that interval is at the point 4, 1. Now this is a point. This is not an interval, it's a point, so we use parentheses, okay? This is the interval. This is just the point right here and right here. Okay, the minimum occurs at the point 4, 1. We get to include it because we get to include x equals 4 because of the bracket. Now let's throw some curveballs in there. How about 1, 4, and the 4 is up against an open parenthesis. So that means you can't include 4. Well, we still have a max because we get to include x equals 1. That occurs at the point 1, 4. All right, because we get to include that 1. Remember, when there's an interval, it's talking about the x values, not the y values. So 1, 4. The minimum is none. This is a always declining function. We're up against an open parenthesis, so that would be an open circle if we were to draw a circle there. And so we don't have a min when x is 4. All right, let's reverse this process and put the open interval up against the 1. Now you tell me, do we have a maximum at the point x equals 1? The answer is no, because we don't get to include 1. All right, so we can't say the maximum is 4 there. How about a minimum? Take a second and answer it. Okay, the minimum does occur at the point 4, 1 because we get to include x equals 4 in our interval, and the minimum value is y equals 1. The y value there at 4 is 1. All right, and then D, it's all open, both sides. So the answer is no max or min. Okay, so use 34 to answer 33 and 35. Hopefully you can get those answered. Okay, the homework from section 3.1, and these are short problems in terms of, there's not, you're taking derivatives and setting them equal to 0 and then reading graphs. But the homework is on page 160, and then it goes into 161. You can do 1, 5, 7. So on 1, that's a graph, and you'll plug in, all right, you'll take the derivative and plug in the x value at the extremum, that minimum at 0. So 1, 5, 7, 11, 13, 15, 17, 22, 23, 25, 29 through 31, I know this looks like a lot, but it's really not. 33, 35, 48. I'm going to give you a hint on that one. 53. So 53, we're bumping all the way over to, and 53 is just true or false, and 54. Okay, so for 1 and 5, you have example 3 that we went over. For 7 and 11, I worked for you example 8. 13 through 25, you want to do 13 through 25. That's just like example 18. So I want you to do it exactly like that. Evaluate the left endpoint, the right endpoint, and the critical point, and then pick out your maximums and minimums. All right, 29 through 31. Look at example 32. For 33 and 35, look at example 34. Do it like that. For 48, here's a hint. Look at the critical points. Look at the endpoints. And then find lowest cost. So you'll be looking for a minimum. So you have to evaluate the endpoints and the critical points on the interval, and then you can find what the lowest cost is on that. All right, that should do it on this. Pretty long lecture on this one. Sorry about that, but I don't think the material is too bad once you get used to it. So that'll do it, and I'll talk to you next video.